colors, and the colors are an indication of the surface temperature. The thing I gave you, okay, so tell me, what kind of star, what type of star that's over here is the sun? Can you find sun? It is a G-type star, very good. And you can kind of see what its surface temperature is. We've been saying 5,800 Kelvin, so it's kind of smack dab in that range. So this is actually kind of nice. This actually is a larger version of what I had on my slide. I couldn't even see that on my slide. So one thing about the colors of stars, that corresponds to the temperature of the star. Another thing is, we talked about, do stars move? Yeah. Remember we said that the Big Dipper actually is going to be, has not always looked, that asterism has kind of changed the way it looks. What if a star is moving towards us? How can we tell it's moving towards us? The spectra, the blue, we'll see a blue shift, yep, okay. What if the star is moving away from us? A red shift, very good. What if the star is moving side to side? That's called proper motion, you just see it. So I kind of butched this, so I thought I would put your finger right in front of your nose and close one eye and then the other eye. We'll put your hand over it then. And what do you see? Is there anything moving? Probably if you're like me, you see your finger move, first it's over here and then it's over here, okay? That's what we call parallax. And the thing about it is, first your eye is over here looking at it and then your eye is over here looking at it, okay? So now go ahead and take your finger, put it farther out and go ahead and do whatever you need to do to have one eye and then the other eye. So what's the distance now? What's the jump like compared to the other jump? It's smaller, yeah. Now we could go ahead, we could make an angle thing out of it. So for me, my parallax angle was small when I had it out here. It was about like that. And for me, when it's close to my nose, my parallax angle was like this, okay? So it changes. So now finally, we're on to some more slides. And we are in part 2B, I think. So stellar parallax looks like this then. And we actually, we touched on this before, this idea of stellar parallax. Now, kind of like we close one eye and close the other eye, we can't do that. But what we can do, haven't done this for a while, is we can, and we do, orbit the sun. Okay, so here, we're up here looking at a star. Okay, 6 months later, we're up here looking at a star. Okay, star, huh? And depending upon how close the star is to us, it can actually kind of, maybe it's subtle, maybe it's not so subtle, kind of change its position relative to the background stars. Unlike the Barnard star, oh, I'm sorry, if you guys watch The Office, you know, the Barnard guy, anyway.
Andy Bernard.
Thank you, Andy Bernard.
Nard dog.
Bernard dog, yes, Nard dog. But what can happen is we'll see it doesn't move, but we'll see its position change relative to the far away stars, what we call the background stars. So here we go, here's an example. Nearby star, now these, let me grab my pencil. The little dots are the far away star, and the big dot is the relatively nearby star. And you can see where that relatively nearby star, so these are the far away stars. They're locked in. But this guy right here, it appears here when we are in January, and it appears here when we are in July. So that will wiggle. That's kind of like, that's like blinking your eyes, and it's moving against the background. Now, that, if it's your favorite constellation, that's really going to mess with your mind, isn't it? You know what I'm saying? Because you literally would see that star move. Well, that's a little bit exaggerated. Probably more to the point, we have something that, oh, sorry, that's, yeah. So nearby star. What happens if we take this nearby star and move it even closer? What happened to, it's kind of like this, closer versus far away. What happened to that distance? It kind of scatters. It got bigger, yep. So this is a nearby star that's farther away, and this is even a closer star. So that angle gets bigger. And if you do the math, you can actually take that angle and translate it to a distance to the star, or up to the star field. So that's it. That's it. Parallax angle. So there are limitations, though. I mentioned subtleness. So it's possible that, 6 months later, we look up and the star has just barely moved. But we called it angular resolution before. If we can't, the more powerful our telescope, the more detail we can kind of see little tiny things. So we need to actually, if our angular resolution is poor, then we can't see these subtle differences in the movement of the star. So which do you think has better angular resolution? If you have a telescope on Earth, or if you have a telescope like the Hubble Space Telescope that's orbiting Earth? The Hubble Space Telescope, yeah. It's got better angular resolution. So angular resolution-wise, we can actually see stars that are a distance up to 150 parsecs. Oh my gosh. So PC stands for parsecs. What did we say the other day? Oh, it's right here. 1 parsec is approximately equal to 3.26 light years. So notice that's with, like, Hubble Space Telescope can do that. Land-based telescopes, not quite the best resolution, but just 100 parsecs. So now we can get distances to stars. And astronomers now know distances to about 2.5 million stars, just by this idea of parallax. I've got a better picture for this. I think I might have told you my list of things I want to do, probably when I retire, is to go to the southern hemisphere and look at the nighttime sky. Yep. Have you seen the southern hemisphere nighttime sky? And my husband's down with that, so that might just happen.
But I know the further that I got closer to the equator, like I went to Abu Dhabi, which is the Emirates.
Okay.
The Big Dipper is almost straight up and down.
Okay.
It's canted just a little bit, but the handle is.
It's kind of striking.
Up top.
All right.
It's kind of
weird.
wild.
Disorienting.
Wait a second. It's usually
right.
East and west, but this was almost straight up.
That's neat. That's neat. One of the things.
Star, the Polaris.
But at least you saw the Big Dipper, and to me, that's one of the things that just I have my heart's really big for astronomy, because anywhere you go, northern hemisphere, you can see the Big Dipper. It's like just so reassuring. So, but. Now, so southern hemisphere, we'd have to go down to southern hemisphere to see this. I'm going to kind of show you what I think is a better picture. This is the picture OpenStax brought. Now, I'm not real thrilled with your author, because this SMC, that's a small Magellanic Cloud. It's a big hairy deer in the southern hemisphere. Actually, it talks about a star cluster. It's not a cluster of stars. It's a whole galaxy of stars. It's a dwarf galaxy. It's a dwarf galaxy. So I'm kind of mad at your author for putting that caption there. Clusters that we saw, ET cluster, globular cluster, those are associated with our galaxy. This actually, the small Magellanic Cloud, I can't say the word, actually is a galaxy outside the Milky Way galaxy. Okay? Do you guys remember, and I'll kind of prove it to you with this slide, how, from side to side, do you remember the Milky Way galaxy, how wide is it? 100,000 light years. 100,000 light years side to side. There's a Monty Python song that says that. Okay? So 100,000 light years side to side. And actually, they're talking about the distance between this, and it's a dwarf. This is a dwarf galaxy. We'll talk more about galaxies later. But it's about 200 light years away. So anyway. It's 200 light years away. So I think these are better pictures of it. Well, I'm getting better, I think. So that's a kind of this star field would have been the star field we saw a minute ago. It's a different galaxy. That is so cool. What galaxy can we see here in the northern hemisphere? Andromeda, with it, a little bit with the naked eye or binoculars. Okay, so this is actually stepping back. Sometimes things are more beautiful when you step back instead of focus in. So this is the SMC, Small Magellanic Cloud. This, I'm pretty sure, I didn't look it up, but it's a type of cluster. What do you think? Globular or open? How many people think it's a globular cluster? I do too. I think globular cluster. But this actually is stepping out even further, where this is the small Magellanic Cloud, and they get this in the southern hemisphere, and this is the large Magellanic Cloud. They're both dwarf galaxies, which I read it again just recently that, is this right? They are interacting with our galaxy and kind of doing a dance. Is the Andromeda Galaxy and the Milky Way Galaxy on a collision course? Yeah. And so actually, so these are, we're all kind of one little family. But this might be my favorite.
So if you were on the equator, you could see both, right?
Depends on how far up they are in the sky.
Right.
So I'd have to look at a sky map. That might be the route to go.
You take a field trip.
This is a meteor, the caption said. So this is a streak on tape. And so this is a small, this is the large Magellanic Cloud.
Looks like it was a field goal. Right?
It does. 10 or 2 points, extra point, 3 points. So, yes. And we'll be talking more about galaxies, but I wanted to make sure we're all on the same track. So back to our own galaxy. Well, we assume that this sort of phenomenon of star building and star buddies happens with stars in other galaxies, but most stars have a companion, and it just makes me smile. Okay, stars have a companion. Sometimes they're a trio, sometimes they're a quartet, and we just call that, if there are two, we call it a pair of binary stars. Now, some stars, and I can't remember how my slides kind of revealed this, but some stars are literally close together, and they orbit a common center of mass. Gravity keeps them doing this sort of thing. But honestly, some stars are just kind of, from our point of view, they kind of look like they're near each other. We call those optical doubles. They're not really near each other. So there's that distinction. But I want to kind of focus on the ones that are really, truly close to each other. So pair of binary stars, how do we know that they're there? And just because of how we know that they're there, they fall into these categories. So these are all binary stars. For instance, we have the visual binary star. Again, the only thing that differs is how we know that there's two stars there. The visual binary, here's an example of, you can actually kind of see the dance being performed between these two little, the white and the blue dot over time. Okay. So over time, you can kind of see them, and if you knew what you were looking at, you could actually kind of infer and understand the math and get a sense for what's going on. They are orbiting a common center of mass, just based upon what you're seeing. So that's a visual binary. The next, oh, here's another visual binary. Actually, what's this right here? The yellow? Yep, the yellow's a Big Dipper. And this is the handle, obviously, and here's the bowl. And the second star from the end of the handle actually is something, when we go out to the observatory and I'm looking for something to talk about, it's a pair of stars called Alcor and Mizar, where Alcor, I think, is the rider and Mizar is like the horse. And so a lot of times, just at first glance, it looks like one, but through binoculars, it looks like two. And if your angular resolution is good of your telescope, you can actually break it out into a quartet. So when we start to talk about how stars are born, we're going to see that, and I already talked about this idea of a stellar nursery, like a bunch of stars can be born at a similar time in a big old cloud of gas. And so you can almost kind of see where, well, they kind of just hung out together. So those are visual binaries. The other one is a spectroscopic binary. Do these look like, and it might be hard for you guys to see back there, but these are spectral, these are spectra from stars. I'll kind of refer you to this. Remember we talked on Monday, the idea that those ladies actually took spectra from stars and put them into these 7 categories that end up, oh, be a fine guy, kiss me, right? So stellar spectra, you can kind of see, well, first off, well, actually, do you guys remember we said that the spectral lines, if something's moving towards you, you'll get a blue shift, and you told me the lines would move over to the shorter wavelength. If something's moving away from you, you'll get a red shift, and the lines will move over to the red part. And that's actually what we see here. So this isn't a visual binary, but you can see this this blue one, okay, right now, so how do I split? I'm gonna put us right here. So this is the Earth, okay? Now when the star is moving like that, you don't see any shift. But when the star moves like this, you would see a red shift. Okay, we're right here, we would see a red shift. When it's moving like that, nothing. When it's moving like that, we would see a blue shift. So what they see are these lines kind of going like this. These lines, these spectral lines, you'll get the red shift away, blue shift towards. I don't know if I'm doing that right. Now just do one pair. Okay, so blue shift towards, red shift away. So it's kind of like mesmerizing. So that sort of information, I just am amazed at scientists of just grasping it. That feels like straws, but I mean it's more than just straws. It's like we're trying to glean every information we can. We can actually see that Doppler effect in the spectral lines. So in a spectroscopic binary, you can't see two until you look at their spectra. There's one more type of pair of stars that you can't see with the naked eye, and it's called an eclipsing binary. Again, the name only describes how you know that there's two stars there. So last August, of course, we had the solar eclipse where the moon passed in front of the sun. If we were to, here on Earth, have a light meter, okay, we'd see bright light, dimmer light, the most dimmest, and then it would start to get brighter and brighter again, okay? That's how eclipses work. So down here, on this little figure down here, I've got the light meter going. So what happens, see, can you guys see that? Oh. Yeah, sort of, I guess. So right down here, okay, so let's just say that the orange one doesn't move, but you kind of see a blue one moving, orbiting around it, but you can't see a second star. Again, those aren't planets, those are a pair of stars. So as the star goes in, as the star over here is totally to the side, we get our most amount of light. Now for the second one, you see the blue star moving in front of the red star and the light goes down. Now you see the blue star moving to the right of the red star and we get maximum light. Now you see the blue star hiding behind the red star from our perspective and we dim the light the most. Okay, so this is a light meter down here. So it's called an eclipsing binary. That's how we know there's two. So again, they're all binaries. They're all real true binaries, not just optical binaries. Pretty exciting. I looked at this figure in my office and I'm like, I don't know. So anyway, if I were to ask you the closest star, you would tell me there was a movie where the little tall blue people went.
What, Avatar?
Avatar, yeah. What planet? What? That was in the movie too. But I'm thinking of Centauri, Proxima Centauri. Like the constellation, the center, Centauri, there's a star called Proxima Centauri. I don't know.
That's Avatar is better than the other Avatar.
I haven't seen the second. Is there a second one?
No, I'm not. I'm talking about like the Airbender Avatar. That one.
Oh, okay.
There is a second one coming out, though.
There is a second one coming out. Okay. Anyway, so this is Proxima Centauri, and your author is kind of, from what I can tell, kind of stepping back to show ultimately there's three stars. It's not a binary, it's a trio. One of my cool things, again, at the observatory to look at is there is a cool double in Lyra, the constellation Lyra. Okay. This actually is a better look at what I tried to describe to you. This idea of being able to see stars in their stellar spectra that are moving towards you or away from you. So here we have A is moving towards us. So what sort of shift would we expect for A?
Blue shift.
Blue shift, yep. So it's over here, short wavelength. B is moving away, red shift. What about here? From our perspective, the blue lines kind of show you the motion. What sort of shift would you expect?
No shift.
No shift, that's right. And you see no shift. So they're going to continue orbiting. Again, what are they orbiting? Something invisible called a common center of mass. They're just orbiting a common center of mass. So now what do we got with B? What sort of shift? Blue shift, yep. And A? Red shift. So you can kind of see them split out. And then to finish it off, what sort of shift do we have? No shift. So this would be a spectroscopic binary. Okay, you may not be able to resolve two stars here, but through their stellar spectra, you're like, oh, there's something going on there. Okay, and this is an eclipsing binary. These are better, much better than my small, tiny things. Okay, so at position 1, what do you think about the light? So we have two stars, we have that big red one and a tiny blue one. What do you think about the light position A? Or sorry, 1. Should be pretty high. I see no eclipsing at all. Yep, so for position 1 on our light meter where we're up here. What about position 2? Eclipsing. So I'm thinking it goes down. Yep. What about position 3? No eclipsing. Actually goes back up to the same as it was position 1. What about position 4? Eclipsing a little bit, a tiny little bit. Yeah, because it's taking, this disk is taking a little bit of the light from the disk, little disk of the blue is taking a little bit of the disk of the red. So yep, eclipsing binary. Look at the light curve. Okay. Well, okay, so this is my tumbling, this is my orbiting a common center of mass. If you can get a fix on this, you can apply Newton's laws that actually kind of backtrack to masses. Because one of the characteristics of a star we need to know in order to understand kind of the science of the star is how massive it is. So if we can do this, okay, observe how it's moving, dancing, okay, we can understand masses. That's it. So in astronomy, what works well is to use the symbol M for mass in the subscript, or the word sun. This is the mass of our sun. So we can kind of talk about other stars in terms of how massive they are. So generally speaking, the most massive stars are 100 times the mass of our sun. Sometimes instead of saying the mass of our sun, we'll call it solar masses. Okay, mass of our sun, solar masses. The dinkiest stars, the lightest stars, and we'll talk about why there is actually, if you get too light, you're not going to be a star, is actually 8% or 0.08 times the mass of our sun. That's kind of the ranges we see. So one of the things, so this talks about temperatures. This third thing talks about how hot these O, B, A, F, G, K, M, L. Wait, I don't do the L, T, Y. Wow, there's more stuff on there. I just stopped with M. O, B, a fine guy kissed me. So if you want to draw a line right there. That's pretty cool though. These to me look like brown dwarfs. Draw a line right there. So what I started to say is we definitely have hot stars here and cooler stars here. Now, we talked about what color are hot stars? Blue. What color are cool stars? Red. Cool. And then the other thing we talked about, and this Stephen's law maybe, is which stars should be brighter, the hotter ones or the cooler ones? The hotter ones should be brighter. And that's all this slide is kind of pointing out. Is aside from kind of some miscellaneous red ones, the brighter ones are kind of the bluish ones. And the dimmer ones kind of have a reddish color. So. Okay.
Do you see stuff like that in at the
observatory?
Yeah. Is it kind of like that or what?
At the observatory, usually we're focusing not in on a star, but some sort of like nebula or galaxy or planet. So yeah, this actually to see, I think the best way is just with binoculars, maybe. Yeah.
Infrared.
Yeah.
Night vision goggles and pulls out, so it's pretty amazing.
I can imagine.
Yeah.
Actually, that's a good segue to, this is looking, see, I read the caption at my office. I believe, yeah, this is the, I thought it was taken in infrared. It's a brown dwarf. Maybe it's visible. But these are a pair of binary stars over time. There they are in April, February. You can kind of get a sense of their dance. October, different year. Now, that's all well and good, kind of the stuff you see on the spokes, but each one of these, and I should have emphasized, each one of this, how do I say, this observation matches up with this figure here, where this is where the outer star is, must be the less massive star orbiting a common center of mass in here. So our common center of mass would be like here probably. So anyway. Speaking of common centers of mass, if you do have a pair of stars that aren't equal in mass, this probably makes sense to you. Where they're orbiting is going to be closer to the more massive one. All right. The next part, and we are going to get to it today. I don't know if we'll get through the entire part C for characterizing stars, but the next part we're going to definitely kind of do some plots. Scientists love plots. I worked at a coal research facility in Morgantown, West Virginia for a little over a year. That's where I met my husband. And he, what the guy I worked for would take coal, and he would look at different characteristics and just plot them and try to find trends. So here we actually see an important trend. Let's look at what it says. Okay, so this is actually, each dot is a star. So from left to right, we're getting more massive. So what do you think then? Going up along the y-axis, what happens is you increase mass. It gets brighter, that's it. Luminosity is brighter, yep. As you increase mass, it gets brighter. And that's a good trend to know. Okay, so so this part will be due when we meet again on Friday. Let's see what we got for the last part. Have you guys ever heard I'm going to totally butcher this, but calculus was invented by, is it Newton? And then, was it Lorentz, who was co-inventing calculus? I don't know how you invent calculus, but at the same time. That's kind of what we have here with these two guys, okay? So these two guys are in different countries. They are astrophysicists, I guess is what you call them today, dealing with stars. And they were getting data on stars, and they were looking at how these two variables would fit each other. And let's see if we can kind of come up with how they would fit each other. They were both looking at luminosity and surface temperature. Now, before you say what you think it looks like, let me tell you what this important plot's going to look like with regard to our axes. Okay. I wonder if, I thought I had a second one. Maybe it's this one. Okay. So we're going to go ahead and make luminosity along the y-axis, just like you saw luminosity. Goodness gracious. And we're going to go increasing luminosity, which what means increasing brightness, right? So the other thing is temperature, and what we're going to do, and today finally I was like, oh my gosh, that's why people struggle with this, because it's like, it seems so backwards. You would generally think we'd go temperature cold to hot, right? No. We're going to go hot to cold, and these are stars. Even the cold star is pretty hot, isn't it? Okay. Cool. So just based upon, and I guess now I'm thinking about it, like what a big to-do that was. What do you think? Hot stars, will they have high or low luminosity? High. That's my star. Cold stars, will they have high or low luminosities? Low. you have just started drawing what's fancily called HR diagram. And that comes from Hirschsprung and Russell. Okay, so I'll go ahead and fill in some. So you would think as it's getting cooler, the luminosity should go down, right? I'm just going to go ahead and make X's. So Hirschsprung and Russell independently came up with this. Now there is a twist on it, so I shouldn't make too much fun of them. Okay, and I honestly don't know why they put the hot stars here, but they did. Oh, before we go on. So in this thing that I gave you, the 7 spectral types, somebody tell me what is the hottest spectral type? Oh, very good. What is the coolest spectral type? Not the other 3, but the cool. M. Yep. Very good. So O, B, fine, guy or girl, kiss me. Okay. We good with that? That's an HR diagram. Totally an HR diagram. Bless you. So Hirschsprung and Russell, each of these dots is a star. You see the sun right there. If it's G, that makes sense, okay? You see the temperatures are hot, going to cooler. You see increasing luminosity here. Yay! It's a Hirschsprung-Russell diagram. Now, we'll be talking more about these, but there are a few terms. I'll go ahead and circle them. I'm going to circle the terms that are written in capitals. So main sequence. This right here, even we're really smart, right? We are really smart. But these are main sequence stars. Up here, there are some miscellaneous stars. They are, I sometimes call them I call them just giants or supergiants. I kind of lump them together. And then, oh my gosh, I love these guys down here. These are some of my favorite. There are some miscellaneous guys down here that are called white dwarfs. I think that about does it on that one. So help me out. White dwarfs, what would you say about the luminosity of a white dwarf? High or low? Kind of low, very good. What would you say about the temperature of a white dwarf? Still kind of hot, yep. We'll talk more about those. As I put a number 1 next to main sequence, number 2, especially next to giants, and number 3 next to white dwarfs, as I've numbered them 1, 2, and 3, those are actually life cycles. We'll be talking about life stages, I should say. Stages of the life of a star. Not all stars go through these. They all start in main sequence, and then they all go, not all of them, most of them go giant, or supergiant, and then they either blow up or they retire into white dwarfs. Yep, that's it. Cool. So scientists are notorious for, it's called a scatter plot when it starts out anyway. They basically just take data and they throw it up on a graph and they say, well, do I see a line? Do I see a curve? Do I see any relationship? So not bad. So these dots actually then represent stars, and not only just any stars, but hopefully start to kind of be thinking along these lines. This is a time in their life. This is like, I don't know how you call it, a person's stage, but this is a stage of their life. What else do we have? For main sequence stars, the most massive stars are hottest and most luminous. Actually, that's kind of consistent with the last slide that we just ended up with in the previous part. For most sequence stars. So in other words, if this is my little diagonal, which one's more massive, upper left or lower right? Upper left, yes. So this is most massive. And you can kind of see it on that diagram by the size of the orb up here. And actually it says 60 times the mass of our sun, 30 times the mass of our sun, 10. And you can actually, they're trying to show you the little circle getting smaller, so the stars getting smaller. Yep, most massive, least massive. What else we got? What those stars? The most massive stars, the more massive the star, the faster it will live its life. So these guys, okay, they better enjoy each moment because they're gonna, and it's kind of like a peeling off thing, because I told you number 2 was over here. So literally we will see these most massive ones peel off and move. It's called move on the HR diagram. So these guys over here, what would you say about their luminosity, high or low? High luminosity. What would you say about their temperatures? Low. Yeah, they're cool. Yeah. I've got a good video on stars, so we'll probably have to take a look at that. And it's funny, like Barry asked about, like at the observatory, is that kind of what we see with maybe through a telescope? But I think stars are underappreciated looking at stars through a telescope, because a lot of times we don't look at stars through a telescope, but we probably should. Mass of the star indicates which stages it will go through. So I'm kind of giving you a little bit of a precursor for when we talk about how stars live their lives. So what's happening in the core of our sun? Fusion. Yep, exactly. What element is being fused? Hydrogen. Yep. Is it going to run out of hydrogen? What do you think will happen when it runs out of hydrogen? So you told me it's creating energy by fusing hydrogen. What if it stops? What'll happen to the temperature? It'll get cooler, yeah. What'll happen to the size of it if it gets cooler? It'll get smaller. And it's a weird sort of thing if you watch these videos. As this inside, as it gets smaller, actually kind of the outside bloats out. So we kind of have this sort of thing going on. Where up here, you guys told me these are luminous and cool. They are luminous and cool. Okay, it's a star that's left the main sequence. And kind of drawn to scale, what this tries to show you is, let's see, orbit of Mars, orbit of, Mercury, maybe is what it says, I don't know. This is just trying to put things in perspective size-wise. White dwarf, what did I tell you a white dwarf is? It's what? Yeah, a white dwarf could be step number 3. It's like the end. It's retired. White dwarfs, what we're going to find out is, I'd like to be a white dwarf. We're going to find out that white dwarfs are not fusing hydrogen in their core or fusing anything. We'll talk more about that. That slide seemed a little out of order to me. Scatter plot. Does it look like a scatter plot? Yeah, too many dots, but each dot represents a star, and what we do with scatter plots is try to look for a pattern. So it's a little more fuzzy than just my strict diagonal I put up here. But this is an HR diagram. Again, get your bearings with what an HR diagram is. The weirdest thing I think is along the x-axis, the hottest star over here and the coolest star over here. Okay, otherwise it's luminosity along the y-axis. So what we have to do is to try to kind of, and it's not even straight. Does it look like it has a little bit of a wiggle? And it does. If you you wouldn't draw a nice straight line like I drew, you'd kind of do a little bit and you'd see the trend as main sequence stars. And then you can kind of see this patch here, patch here, patch here. Cool. Oh yeah, now I have a little video. Because I don't think this does justice. What this slide is trying to do is to kind of say, you guys told me G, you told me our sun is a G-type star. And this video I'm going to show you, you may have seen it before, it kind of puts in perspective the size of our sun versus other stars. So, let's see. So we talked about binary stars, companion stars, and maybe this is what I think Barry was talking about, infrared, seeing things in infrared. Well, this is the dog star, Sirius, which is a really bright star these days. So Orion, and then you see Canis Major, and Sirius is there. And it's got a companion, but its companion is retired white dwarf, so you can't really see it. But if we switch it to infrared, there she goes. She's hiding in the glare. This truly is a globular cluster. I love globular clusters. They kind of have this beehive look to them instead of open clusters. So this actually, if you look at distance, 28,000 light years, it's a far piece, but it kind of puts in perspective of our 100,000 light years side to side. That actually is our galaxy. So that's all good. So I want to summarize a few things we've been talking about. So luminosity is how bright something is. Okay. I shouldn't say that. Luminosity is how much energy something's putting out. And we can get from luminosity, we can get luminosity from how bright something appears and the distance it is away from us. So, of course, the L sub sun means the luminosity of our sun. So 10 raised to the negative fourth, how would you write that as a number? 10 raised to the negative fourth. How about 1 times 10 raised to the negative fourth? What is that? Yeah, and the fact that that's a negative means it's 1/10 times 1/10 times 1/10 times 1/10. So 10, this right here means 0.0001 times the luminosity of our sun. Does that make sense? How about 10 to the 6th? What's that mean? Yeah. What, 1 million? I get my millions and billions mixed up. 1 million times the luminosity of our sun. Okay, so kind of keep those in mind. We can know surface temperature from its color and its spectral type. Oh, sorry. So in blue here, I said luminosity-wise, the low luminous ones, does this make sense? The low luminosity ones are the lighter ones, and the high luminosity ones are the heavier ones, massive stars. Okay, so let's do, what are these blue numbers going to be here? So what about the cold stars? Are they going to be massive or low mass? Low mass, yep. And the hot stars are going to be high mass, yep. Okay, and again, kind of the ranges of stars we see are 0.08 times the mass of our sun and 100 times the mass of our sun. So again, this kind of gets a little bit into what we're going to talk about, how long the life cycle of stars. Just a minute ago, what did it say with regard to massive stars? Do they have long lives or short lives? Short lives. Massive stars have short lives, exactly. Something the size of our sun, this G-type main sequence star, it actually, once it became a main sequence, the star, its clock started ticking, and it had 10 billion with a B years to go ahead and fuse hydrogen into helium. We're about halfway through that. So now what if instead of the size of our sun, we upped it tenfold? So 10 times the mass of our sun. What that does then is it actually decreases instead of 10 billion, it only has 10 million years to live. 10 million. Okay, what if we go the other direction and we went a lower mass star than our sun? Instead of 10 billion, actually it's going to have 100 billion. So this seems like this should be, this one doesn't seem, I buy this one, 100 billion years. So a star, that just is amazing, 100 billion years to be a main sequence star. Okay, so now both of those will be due on Friday. So this put us at a good spot for Friday's lecture.
What section is that called?
What's that?
What's the section number?
What's the what?
The section number?
The section number, we just finished C32C. Thank you. 32C, but we did 32B also. Yeah.
Yesterday, I forgot to take, sorry, I forgot to take a